Okay, hello, my name is Ignat. I work for Cloudflare. Does everyone hear me? Yes? Okay, so today I'm going to talk about how to manage secrets at scale with a Vaultless password manager. First, a little bit about myself. I'm a platform engineer in Cloudflare, so I'm not actually an ops or SRE person. I do half and half, like development for operations or operations for development, if you put it that way. I'm passionate about security and cryptography, and I also like low-level things, so I like C programming, kernel code, firmware, and other like very scary things where everything can go wrong. A little bit of disclaimer here. So the talk I'm presenting is mostly applicable if you manage physical servers. So if you have your real data center with real hardware, if you use some kind of a cloud provider for your service, most probably your cloud provider should give you a better way of managing secrets in its cloud, and if it doesn't do that, then consider changing your cloud provider. But as the logo says, there is no cloud, so even if you do use a cloud provider, that cloud provider is responsible for managing physical hardware, and it probably has the same issues, so it's applicable to him. And if you see that your cloud provider does not effectively manage secrets in its cloud, then forward my talk to them. Okay, so imagine you have a server. You're starting a new project, a new service or a platform, and you have a server which you run it on. So what's the minimum set of secrets or keys you might need is a server, like the basic set? So the first one is you probably need an SSH key. First of all, you need to log into your server securely, you need to debug things, you need to do maintenance, you need to, I don't know, perform day-to-day operations if you do it through SSH. So most probably you need an SSH key. As your service grows, you're managing more than one server, you should consider using some configuration management system. So any company or any service uses some configuration management system in one way or another. It may start as like in-house built-in set of scripts, but most like larger companies use some commercially available or open source ready-made configuration management system like Salt, Ansible, Chef, or Puppet are the most popular examples. But regardless of which configuration management system you will use, all of them, if they are sane and secure, will require some kind of a key infrastructure to support, because you don't want to deliver your configuration to any hardware. You want to deliver your configuration only to your hardware. So you probably need some kind of a means for your configuration management to authenticate your managed servers, and your managed servers to authenticate the configuration management. So there is probably some kind of a key infrastructure here, so it's a configuration management key. The next one is disk encryption key. So if you process user data or even if it's your internal data, you should consider having it encrypted at least at rest. So, and the most popular solution would be to just encrypt your disks completely. As your service will grow, it's hard to find services which are self-contained and in one piece of, or like in one data center of a set of hardware. You most probably still use some other third-party services or APIs to offload some of the tasks or to integrate your service somewhere, like, I don't know, Salesforce or any other, like with Google or any other like readily available services provided there. But if you use some kind of an API, you definitely will need to use some kind of a credentials to authenticate your server to this API, and that you also need to care about on the server. And there is probably more. So this is only the basic set of secrets you might have in your server. Most probably, depending on what your service will do, you will have more than that. So it's at least 5 keys or secrets, and that's per server. So imagine as your service grows, and now you have a data center, and your service grows more, and now you have 2 data centers, and you grow more, you have more and more data centers. So for example, this is a Cloudflare network today, so we have more than 100 data centers across the world, and one of the biggest data centers may have like more than 100 of servers in each of them. So it's like, in the end, it's thousands of servers. And if you take a look at key management server, it looks something like this. So you're like a big key master with a lot of keys to care about. So what can you do about that to make your life easier? So let's take a look where keys usually live. So one option is that you may store your keys on your local persistent storage in your servers. Another option is you may store your keys or secrets in your configuration management system. In Cloudflare, we use Salt as our configuration management system. Anybody familiar with Salt here? Oh, good. So I will, my examples in this presentation will include examples from Salt, but they actually are applicable to other configuration management systems, and most of them have similar set of properties and features regarding secrets. So let's say you decided to store your secrets in configuration management system. By the way, during this presentation, although the example says keys in the title, but I show an example how to store root password. When I say keys, secrets, or passwords, I actually mean the same thing, so some secret per server information. It doesn't matter whether it's really a key or a password, it's some information you want to keep secret on your server. So this is an example from Salt Pillar. So Salt Pillar is actually a simple key value store which can distribute configuration to its managed servers. And with Salt Pillar, you can just encrypt your key with PGP, and it will be distributed, and your Salt Master, which is your configuration management server, will decrypt it on the fly before distributing the values to your managed server. So the servers will actually receive like unencrypted root password and can apply it. But with configuration management system, you have chicken and egg problem. That first one is how do you bootstrap your configuration management system? As I previously said, every configuration management system requires some set of credentials to actually mutually authenticate managed servers and the configuration management itself. But if you want to manage keys via configuration management system, how do you manage key for the configuration management system? And also, it doesn't scale enough for unique keys. So in the previous example, I showed you how typical root password would be encrypted in the Salt Pillar. But that means that every single one of your managed servers will get the same root password. And when you tell your InfoSec department about it, they will just be, whoa, no. This is not secure. We want that every server should have a unique password. And this is like same security requirement. It's just to reduce this risk of compromise, because if you compromise one server, it doesn't mean you compromise any other servers. But it's a burden for operations. So if you want to support unique root password for a configuration management system, you end up with something like this. So you now have to differentiate from each server, and each server will have its own entry of the root password. And imagine if you have thousands of servers, you will have thousands of if clauses in this file. And you also, when you provision new servers and add capacity to your overall clusters, you have to not to forget to add entries in this file with new passwords. Another problem here is key rotation. So the same InfoSec department will come to you in 6 months and they will say like, oh, by some compliance requirements, we are required to rotate root passwords every 6 months. And imagine you have, again, thousands of servers, so you have to regenerate thousands of passwords and to update this file and distribute the configuration. So it seems like storing secret contents, even encrypted in configuration management, is not very scalable or a good idea, at least with current features of modern configuration management systems. So another option is you can store keys on local disk. And the way to automate it, so you not just set the keys on local disk, you want to just servers to auto-provision themselves. So you just do, this is the most typical solution I've seen. So people have like these startup scripts where they, in their like operating system images, where they, when they're executed, they see this, the server is new. It doesn't have keys yet, and they just generate keys on system boot. And if the keys are available, they just use them. But one caveat with this approach is entropy. Without any precautions, if you just read from operating system random number generator, you may have, it may still have low entropy on boot, and you may end up having weak keys. So it's a rather dangerous approach. And also you have some chicken and egg problems. This approach is not very suitable for some key or secret types. For example, the same root password. So although you can have an automated script will generate a random root password on your system boot, you actually need some means to know this root password to be able to use it later. So then you have to come up with some kind of idea of password collections, or I don't know, send this password somewhere, but to send this password somewhere securely, you again need to establish a secure channel, and you need to have some secure credentials to establish a secure channel. It doesn't play very well with disk encryption because ideally, if you store keys on local disks, you want to apply disk encryption, you want to encrypt those keys, but you want to encrypt those keys, you need another key, and where do you store this key? And if you encrypt it with another key, it just goes indefinitely, so you need to store the final key somewhere. And also, it prevents you from bootstrapping your configuration management daemon early in boot, because if you store your configuration management credential key on the encrypted disk, it means you can't use your configuration management system to unlock encrypted disks. And it means that you should devise some other means of unlocking the disk before even your configuration management system can kick in after boot. And also, what about diskless or stateless system? At Cloudflare, most of our servers are booted from network. They are stateless, not in the way that they don't have any disks. They do have disks, but it's much more convenient to have a stateless image. And we clearly separate core code from the data. It's the same as if you develop like microservices on Docker. You probably will run the database in one container and keep the actual data in another container, like which call a data container. It helps you to decouple code from your data, and then you can upgrade each part individually. But if you consider diskless system from key management perspective, you don't have any persistent storage to store your keys. So that means you have to come up with some way to, that means your credentials will change every boot, and you have to come up with some way to like validate them in runtime. So if you do have disks, most of the people end up having this solution. So with disk encryption, they encrypt all the disks but one, or they encrypt almost everything but one partition, where they just store the keys for the other disks in that unencrypted partition, which is not very good from security perspective. So it seems we don't want to store the contents of secrets in your configuration management, but disks also are not very good solution because they have a lot of these chicken and egg problems. So is there any other standard storage on your server which you can utilize to store key information? And if you take a look at UEFI, which stands for Unified Extensible Firmware Interface, you will actually find a lot of useful features. So what UEFI is, it's also known as BIOS 2.0. As we all know, like BIOS was developed like in 80s or something, and it was developed for one specific type of hardware, but somehow adopted across different types of hardware, but it has many limitations. And so UEFI was an attempt to actually provide a new interface which is more generic, easy to use, and which will support almost all types of hardware and even different types of CPU architecture. So it's UEFI, it's a standard pre-operating system environment. So if you do UEFI boot, most probably your bootloader works on UEFI. It is extensible, so it has a simple standard C API, and you can write your applications on top of it, and they do not have to be bootloaders only. You can write any application for these interfaces. It is nowadays supported by all major operating systems. So because it was developed some time ago, new versions of the specification are being introduced, but most of the time it's more or less compatible with what was introduced before. And UEFI, unlike BIOS 2.0, is much more advanced and provides some advanced feature. For example, you can even have networking, HTTP protocol in UEFI. And the other interesting popular thing in UEFI is secure boot, which is extensively used by Windows and Microsoft, but is also very useful in your server deployment, secure pipeline. But we will talk about an interesting feature called UEFI variables. So what are UEFI variables? It's just a simple region of flash memory in UEFI chip backed to store, which can be used by users or equipment manufacturers to store custom data. And it's available to users as well, so you can store your data there. And the convenient point that this data can be accessed not only before the operating system kicks in, but even after. So it's data available like throughout within the normal functioning of operating system. And it has a very great support in Linux. So it's built in. To utilize UEFI variables, you don't have to develop any additional tools or software. It's all there. So this is a typical example. How do you access UEFI variables from Linux? Linux kernel has built-in special file system to access UEFI variables. So once it is mounted, you can mount this file system yourself. You can just access all the data in UEFI variables as regular files with some additions shown on the slide, but still it's easy and scriptable. And if you use a recent modern systemd-based Linux distribution, so UEFI variable file system is mounted by core systemd code very early on the boot stage. So the advantages of UEFI variables, they're always available. Since this is a part of standard UEFI specification, you can expect that this feature is available in your hardware. It can be accessed in very early boot stages. So UEFI variables are mounted by core systemd code even before systemd starts to process your boot script. So it means you can rely on this data already be available when your system boots, even in your startup script. The only downside is, as we have to remember, this is like a reserved portion of a small flash memory chip, so it has very limited storage. You can just put some tiny bits and pieces of information there, not like the whole files or something. But it seems it's a very good option to store your keys because it's already there, it doesn't rely on any disk support, and it's local, it's easily accessible and scriptable. But the only problem here is how do you store many keys there. So you can probably store 1 key, 10 keys, maybe even 100 keys, but if you're at some point you want to scale that, if you get a requirement that all your services or even every instance of your services of every container should have a different credential, how do you scale to that point? To do that, we will look back how cryptography works a bit. Unfortunately, the first potential solution which comes into mind may be that, oh, let's just compress all the keys. But since keys are just random data, they are not easily compressible. I can't actually compress the keys. You can try it yourself. If you do compress the keys and you succeed, that means your keys are weak. So please rotate them. But it is possible to derive keys. Deriving keys means that you can generate a key, and it kind of like a compressed archive of millions and millions of keys, and you can extract keys one by one from there if you would like to. So, in reality, if cryptographical properties of keys guarantee that if you have one very, very strong, truly random key, you can actually derive as many keys as you want from this key. And all of these keys will also be random and secure. And this is a great option. And this is how deterministic password managers work, or as I call it, vaultless password managers. So vaultless password managers are based on two basic operations. One is KDF, a key derivation function. So the way how it works is if you have this master key, which is strong and secure, you put it as an input to this KDF function, and you can also put some additional information. It's called salt or additional info or just info as a second input to this function, and you get another key, which is also secure. And the nice thing about it is that if you variate this additional input or salt, you put a string 2, for example, here, you get totally different unique key, which is also secure. And you can repeat this process as many times you want to get as many keys as you want. And the security requirements here that only the master key should be kept secure, but these string 1 and string 2, they can be just public information. So another operation is deterministic cryptographic random number generator. So this scheme shows how to derive, like, master key here is just a piece of a blob of random bytes, and you can just derive another piece of random string or bytes or a binary blob from it. But for example, for SSH, you need a cryptographic RSA or ECDSA key pair. So that's where deterministic random number generator come in. So what it means is you can seed this random number generator via static seed, and you can get your key pair. And if you seed it with another seed, you will get another key pair. And this this process is totally reproducible. You can always put seed 1 into this deterministic random number generator and get key pair 1. You can just recover keys like that. So combining these two primitives, we developed a tool called GoKey, which is exactly a deterministic password manager. So again, to recap, a deterministic password manager, unlike normal password manager, when you have a vault, it's like a database of keys, and they just encrypt all your keys with your master key. In deterministic password manager, there is no vault. You just have a master key, and you just derive all your service keys from this master key. So imagine, so the way how it works, we have a master key. We call it master seed in Go key terms. And we have this customizable string. We call it realm. Theoretically, you can put any string there, but it's very convenient that we just input a string which denominates the potential key usage. So if I want to generate an SSH key, I put SSH there. If I want to generate disk encryption key, I put just disk encryption key there. So if you feed it to KDF, in Go key we use HKDF, which is HMAC-based key derivation function. You just receive another seed, and then you feed the output to the deterministic random number generator. You get your SSH key pair. Now, if you need another key pair for a different service, let's say I want key for SaltStack to bootstrap my configuration management, I just change the real stream to SaltStack. So I get another instance, a different instance of deterministic cryptographic number generator, and I get my SaltStack. And SSH key and SaltStack key will be different. They will be unique. And the nice thing about it that this process is totally reproducible. So what I need now, if I just want to store my keys in UEFI variables, I just need to store the master seed, which is only for Go key, it's only 256 bytes. And from that, I can deterministically on boot time regenerate all my service keys as I need them. So a typical process managing keys like that would look the following. So you still have the startup script which generates your master seed on early boot stage, but instead of just reading from operating system number generator, we use the same Go key tool, and Go key tool has special provisions to ensure that before generating the seed, there is enough entropy in the operating system random number generator, so we just generate the seed and store it in UEFI variables. Then we have one simple startup script which recovers configuration management key from this master seed and bootstrap the configuration management daemon. So now our server can easily talk to configuration management system. And later we use configuration management system to recover all other keys. So we just have instructions in our configuration management system say, hey, we want to start SSH, please recover SSH key. We want to decrypt disks, please unlock all the generate disk encryption key and unlock all the disks. And this approach provides some advantages. So we are fixing most of our problems described earlier. So since we don't store any content in configuration management system, we don't need to store this large if-else statement anymore. But instead, what we can do, we can just store the realm or key usages in the configuration management system. So for example, for SSH key, we have only one entry for all our servers to say, here for SSH key, please use our Go key tool and generate SSH key here. Because every server will have a different master seed, this SSH key will be different on each server, but we don't have to add any entries for new servers, so it automatically scales. And even if you add servers later, you provision new servers, you don't have to modify this file. It will just work immediately on your new servers. And another convenient option here is key rotation. So again, if your InfoSec department comes in and say, hey, now we need to rotate all SSH keys across our fleet, as you remember, if we just change this realm string, we will get complete different set of unique keys. So what we do here is just change one string, and we say, okay, we will now use SSH v2. v2 means not the SSH version, but the version of the key. And we apply this configuration to all our servers, and they will immediately regenerate all the SSH keys. And we can also fix this problem, since we do not need to rely on persistent storage anymore to store our keys. We can just encrypt all our disks across all our machines and without any internal dependencies. So the conclusions here, so by using UEFI and deterministic password manager, we can clearly decouple your server key storage from your regular persistent storage. We can also decouple key contents from the key management. So we use key management to actually instruct servers which keys to generate, but we also make sure that your configuration management does not control the key contents of the key, which is good from security perspective. And also, it's much more easy to operate because you don't have to have these like large if-else statements and to provision unique keys for each server. As I said, it's easy to add new keys or rotate existing keys, even if as long as you have this system provision, you have this master seed and the deterministic password manager in place, you can easily add new services. So if you're planning to launch another service on your cluster and you need a new set of keys, you just add another entry with another realm string to your configuration management system, and these keys will be generated for you. Also, as we saw, key rotation is very easy. And better security guarantees. When you continuously regenerate your keys, you have to make sure that your internal number, operating system number generator, was not compromised. It produces valid and secure output and truly random output. But if you use the deterministic approach, as long as you were sure that your master seed was generated securely, you are sure that all of your keys which are derived from that seed are also secure and have good security properties. And our deterministic password manager is open source. We put it on GitHub, so any feedback, comments, I don't know, contributions and PRs are welcome. Thank you.